So I'm thrilled to have Mark Forster joining us in the hot seat today. Mark is the Chief Development Officer of K2fly and has significant experience in the design, development and implementation of complex software systems for large mining organizations. He'll be giving us an introduction to machine learning and how to use these technologies should be applied to geological processes and problems. So thank you so much, Mark, for joining us. It's wonderful having you.
Great, thank you very much. Yeah, I don't know if I'm going to be as entertaining as the last act, but I'll give it a go. Here we go. So yeah, today's talk is all about machine learning. This is a high-level introduction. I'm going to try and cover as much as possible in sort of 30 minutes, and then hopefully we'll have some questions afterwards. So I'm actually going to take a little different approach today. I'm not going to talk a lot about mining and geology. Right at the end, I'll talk about, potential uses in the geology world. But today what I'm going to talk about is just a quick overview on AI and machine learning. We're going to talk mainly about supervised learning, which is mainly about regression and classification. And then we'll talk about how do you prepare your data. And instead of just talking a lot of theories, how do you do this in the real world? What are the important things to do and how do you approach the problem? So as everyone would know, AI is certainly a hot market at the moment in the business arm, in the software industry. It's one of the fastest growing sectors. Artificial intelligence has been around a long time. It's been around literally from post-war, but we didn't really have the computing power and the environments to really make it happen. And obviously there's a number of things that have happened over the last few years. We've got cloud computing taking off, the commoditization of hardware, which is driving a lot of these technologies. So there's a number of branches of artificial intelligence. Machine learning is one of those. Another one is deep learning, which is very closely related to machine learning. It's just a different approach. And then we have the sort of more visible aspects of AI. Those are things like computer vision, robotics, and natural language processing. So today I'm going to be talking about machine learning. There's essentially three types of machine learning. There's what's called supervised learning, which is what we're going to be talking about today. There's unsupervised learning, and there's reinforcement learning. So supervised learning is all about when you have, if you like, labeled data, and I'll go into that a little later on. So that means you're able to train a model, and so it's able to predict that label when you give it a new data set, okay? Unsupervised learning is very much the same, however, you don't have those labels. So, like if you were trying to, one of your things you were trying to achieve was to predict housing prices. It's like having all the data about the house, but you don't have the price, okay? But however, what you can do with unsupervised learning is you can do things like clustering. So based on all the other attributes of a house, you can tell an algorithm that I want to create, say, 5 different categories of houses. And by looking at all the attributes, it would cluster them effectively for you. Finally, reinforcement learning is a totally different approach, which is basically uses software agents to maximize or minimize a target variable. And typically you have these software agents are rewarded based on how closely they're getting to this optimal situation you're trying to drive. So we're going to talk mainly about supervised learning today. So supervised learning split into 2 different areas. You have regression and you have classification, and it's dead easy. Regression really is about predicting a continuous variable, so a numeric variable. So this is the one I just mentioned earlier, the housing data set. So obviously this is a famous data set that's used in sort of universities, etc., to teach people about machine learning. So this is the Boston housing data set. So it has 14 variables or attributes about housing information in the Boston area. And our target variable, as it were, is the median value of owner-occupied homes in a particular area, okay? So what you're trying to predict with regression in this example is you're trying to predict the median value of a house. So the way that it works is typically you've got two main ingredients in creating a machine learning model. You've got the algorithm that you're going to use, which I'll talk about in a second, and you've got the data set. So when you combine those, when you feed all your data into that algorithm, it will create a model for you so that if you were to put a new set of new housing data in, but you didn't have a median value, it would predict the median value for you, okay? So the assumption is you have all the other 13 attributes and it will calculate the 14th one for you based on the model you've built. So there's lots of different types of algorithms and there's lots of ways to configure those algorithms. So some of them you may have heard of, you know, there's things like linear regression, decision trees, neural networks. They've been around a very long time, but there's others that you may not have heard of. We've got things like random forests, which are essentially groups of decision trees. So you use multiple decision trees and to aggregate an answer or a prediction to you know, give you the best algorithm possible. We also have other support vector machines, gradient boosting. Neural networks, although they've been around a long time, they're essentially what we now call deep learning. So they now have hidden layers in their architecture, and they're typically referred to as deep learning, and they're heavily used in computer vision, language understanding, etc. And then once you've chosen one of those algorithms, they have a whole lot of parameters as well. So there's often 50, 60 different ways you can run one of these algorithms. So for example, the nearest neighbor algorithm, you know, some of the parameters there are things like, if you've got a data set, how many data points do you want to use to calculate your prediction in the nearest neighbor algorithm? So you can say, you know, I want to use 5 neighbors or 10 neighbors. And then do you want to use distance weighting? So if you imagine your data set in sort of a 2-dimensional space, there's distances between those data points. And of course, in that previous example, we actually have 14 different dimensions. So you can't visualize it, but that's what's happening. There's a distance between those points. So you can say whether the weighting is uniform or it's distance-based. And then there's also things like distance metrics. And every one of these algorithms has a different set of parameters that can be used. And it's knowing how to manipulate those parameters that drives your best solution, as it were. The other key thing with machine learning is you've got to know whether your algorithm's working well. So, you know, a key part of machine learning is typically what you do with your data set is you split it into 2 sections. You split it into a training data set and a test data set. And then what you do is you run your model. So you take your training data set and you put it through your algorithm based on your parameters. You create a model. And then you actually test your test data set against that model. Now, because your test data set, you know what the actual values are, you just feed in all the other attributes into the model and get it to predict the values. And typically what you are trying to achieve is in this case, what I'm doing is I'm squaring the difference between the predicted value and the actual value and summing all of those up. And then the algorithm that gives me the smallest error is the most accurate algorithm in that case. So that's typically how you would measure a regression algorithm. And we'll see a little later on, it's a good strategy to in fact try different parameters and try different algorithms to improve your prediction capability. So that's talking about regression. Now we also have a totally different type of classification or different approach, and that is known as classification. So now we're not predicting a continuous numeric variable. In fact, what we're trying to do is predict a class. So in this one, this is a very famous statistical data set that's, I think, is nearly 100 years old. A famous statistician used this data to predict classes of irises. So, and it's only got 4 parameters. So, you know, you've got the sepal length, the sepal width, and the petal length and the petal width. And but what it's doing now, instead of predicting a number of some type, you're actually trying to predict a class. So you have quite often used very different algorithms to do that. I've shown an example here where all the input data is all numeric, but that doesn't have to be the case. It can also be categorical. So, you know, you may have, I'm no botanist, but you could have a subclass of plant or something like that, or a species or something that you could also include. But then you'd have to manipulate your data to represent those different categories of plant as numeric values, because all of these machine learning algorithms, they only work on numbers at the end of the day. Another classification problem sometimes is actually sort of natural language processing. So, you know, you can imagine if you use a news site like BBC or Bloomberg or news.com, you quite often go to these websites and the news articles are categorized for you. Now, they don't do this manually. They're using machine learning to do this. And what they do is they take you, obviously there's a categorical variable, that's our target variable. And that's how we know it's a classification problem. So there's 5 categories. However, in this problem, what you've got to be able to do is convert this text into numeric values. So, you know, a simple technique you might use is you might wean out all the common words. You can do a lot in the text processing area. You can do things like remove synonyms or standardized synonyms and homonyms, correct spelling mistakes, take out punctuation. But eventually what you want to do is basically create a matrix that says, for every news article, I want a matrix of the columns in that matrix to represent, say, the number of times that word occurs in that document. And then I can use that data set and feed it into a machine learning engine to predict a classification for us. So classification algorithms. So there's a few new ones here. There's a lot of very similar ones we saw before. A lot of algorithms can actually do both. It depends on, obviously you just tell it, I'm predicting a continuous variable, I'm predicting a category. But then there's special ones like logistic regression, naive Bayes, that are specifically used for classification. So naive Bayes actually is an algorithm that's used heavily for spam detection. Okay, so it's really good at detecting when you have 2 different classes of data. So in that example at the bottom, you've got spam and it's not spam, okay? Naive Bayes is a very good algorithm to do that. And it's a very simple algorithm as well, but it works very well. And again, all of these algorithms have parameters that you can change and manipulate so that you could have 50 varieties, if you like, of a naive Bayes algorithm. They just have different parameters, you configure it differently, etc. Now, with classification, your performance metrics now change because it's actually a lot trickier problem. And so your typical one that everybody thinks about is, of course, is accuracy. So how many times do we predict the correct classification? And that's quite simple. It's just, you know, if we feed our test data set into the model that we've created, and we've got 1,000 records in that data set, if I end up with 900 correct predictions, then my accuracy is 90%, okay, which is, it may be good or bad depending on the problem set, the problem in the data set you're using. But that often doesn't tell the whole story. So for example, if you think about the spam problem, if you had an algorithm that predicted, that just always gave you the same answer every time, it just said it's not spam. Well, in this algorithm, or in this example below, it would actually be correct 92% of the time. So accuracy is not often a good indicator, in fact. And in some fields, for example, medicine, you want to know, for example, if you're trying to predict whether a patient has got cancer or not, you've got to be very careful about your incorrect predictions, because at the end of the day, you know, because it's life-threatening, you've got to be careful about people who have cancer and you predict that they don't, because then you're not treating them. And likewise, people that have it, but you don't detect it. So you've got to look at those metrics as well to work out, how well your algorithm's working. Now, one of the tools that is commonly used, which is really effective, is what's called the confusion matrix. Very bad name, but it's actually quite helpful. It's not confusing at all. So this is obviously the simple two-dimensional problem. So it's basically saying this was my actual data. So this is and when we say actual data here, we're talking about our test data set. And then when I push that data into our model, our machine learning model, these are the predictions it came up with. And on the diagonal are all the correct predictions. So in this case, I got 96% correct. We actually had 8 spam records in our data set, but we only predicted 5 correctly. So you can see our accuracy for actually detecting spam was actually quite low. I only got 5 out of 8 correct. However, in the not spam area, I was much better. I actually predicted 91 out of 92 emails correctly. Where this is really useful is, of course, as you get a larger problem and more classes in your problem. So, for example, that BBC problem we looked at, the BBC News one, that has 5 classifications. So here your confusion matrix would actually be 5 by 5. And you could see, when you're saying that a tech article is being classified as a business article incorrectly. And I remember playing around with that data set. I played around with it last year, and quite often it was actually we ended up with a very good prediction, but the business and the political articles would sometimes get confused because of the text within the articles, etc. But that's how you look at a problem, and you've also got to look at things like, which ones are you predicting incorrectly? Because in the field you're in, that may be very important. Okay, so that's like a very quick overview of machine learning at a high level. What I wanted to talk about now was what's the typical approach you take, and this is at a very high level, and I'm going to get into more detail later on. But it's the same old story. It's that whole concept of garbage in, garbage out. If you're going to train a machine learning model, you have to have good data. So step one is actually to make sure you've got a really good data set. And we all know in corporate environments, that can be quite challenging. In the geology world, data is captured in field, in the pit, sometimes in extreme conditions, and it may not be 100% correct. So you've got to do things like, you should be doing data exploration, exploratory data analysis, looking at your data, seeing if you've got missing data, maybe there's attributes that are missing, and work out what do you do about that. Do you use statistical techniques to reproduce or replace that missing data? If you're doing things like classification, imbalanced data is a big problem. So for example, if you were training a spam detector, then you're going to want, typically if you took an email data set, probably about 3% of it's going to be spam and 97% is going to be not spam. Now, that's not a good way to train your model. What you want is a 50-50 split so that it can equally detect spam and not spam effectively. So if you've got a 15 category problem, maybe you're trying to predict geological material types and you've got 15 different material types, then you want to prepare your data set so that it exhibits those characteristics. So you've either got to undersample the larger data sets or the larger categories, or potentially oversample the lower categories, etc. So you get that balance. So there's quite often a lot of work that goes into that. The other thing is then what you do is, as I mentioned earlier, is you split your data set, and we typically split it. When I work on these kind of problems, I use the 20% as my round number. If you've got a very small data set, sometimes that has to increase quite considerably, because otherwise you don't have sufficient data to train your model and evaluate it. So it depends on the data set you're dealing with. There's this misnomer as well in machine learning that you have to have masses of data. It's not always true. Sometimes having a lot more data helps, but sometimes it doesn't. And I've seen problems like that as well. So what you do is you split your data set. So if I had 1 million data points, I put 800,000 in the training data set, and I put 200,000 in my test data set. And then I go and create a machine learning model. Let's say I'm doing a classification problem. I'll start off with naive Bayes. I create a naive Bayes model. And then when it's created, so you pass it the parameters to the software you're using. And sorry, I should make a comment about that. There's the two key sort of programming languages that are used in machine learning are R and Python. Python's probably the most popular these days. It's very easy to use, and it's where all the latest algorithms come out. So R is heavily used by statisticians, so it tends to be more statistics centric, whereas Python is very much in that artificial intelligence, machine learning space. And there's lots of commercial products out there as well. So they're both open source products, they're freely available. But people like Microsoft now, with the Azure cloud, AWS from Amazon, they all have machine learning software available on there as well. So there's lots of different choices, but Python is a very good place to start. So once you've created you've handed the 800,000 records to the machine learning model, you pass in your parameters, you say, this is how I want my algorithm to run. And what it does is it creates a model for you. And then what you can do is use that model and you can say, right, I've got this test data now. Now fit this data to the model and predict a new set of results for me. So in this case, I would get 200,000 brand new predictions. And of course, what I have over here that I've hidden, as it were, so I didn't pass that to the model, is the test set of labels. So I know what categories they should be. So basically what I'm able to do is I can evaluate that model by comparing my test labels against the predictions that the machine learning model gave me. So by comparing those, I can come up with accuracy numbers, I can come up with a confusion matrix, and I can see exactly how good that model is. So then I might record that score and try again with another algorithm. So I use the same training data set, but now I use logistic regression, okay, with the same data set. And the reason you do that is in machine learning, you have this concept of no free lunch, okay? And what that really means is there's no one algorithm that suits every data set. So you can find, it's quite, you know, the algorithms that do well can vary enormously, depending, and even in the same problem domain, depending on the data set, a different algorithm can work better for your data. So that's the whole approach of this, trying different algorithms and looping through this, this approach, so that you evaluate all the different algorithms, you keep pumping in your test data, and you record your scores. And eventually, once you've tried all your different algorithms, say you're going to try 10 different algorithms, you come through and you choose your best model, okay? Now that's a high level overview. It's actually a little more complicated than that. And one of the things I want to show you is, you know, one of the things I said is splitting at 80-20. Well, just talking about that, first of all, you want to use random numbers to do that. So you want to pick your data randomly. So you randomize your data sets. So that 80% is randomly chosen from your population, and likewise with the 20%. And obviously this is what you end up with here. One of the problems you have with that approach, though, although you've randomized the data, is you could still get a strange situation where this data here is quite different to this data over here, you know, just through sheer randomness, okay? So one of the techniques you use is something called cross-validation. And that is, what we do is we actually take our entire data set and we split it into 5 20% chunks. And then as we run our evaluation each time, we grab the 4 chunks that make up our training data set and our 5th chunk that makes up our test data set. And instead of doing it once against the one algorithm with the one set of parameters, we actually do it 5 times. And the reason for that is on the second time, we changed the 20% of data we're going to use as our test data set, okay? And we keep doing that until we've run it 5 times. And then we can total up our number of predictions and our number of correct predictions to now get an overall confusion matrix. The end result, of course, is what you've done is you've used your entire data set for training of the model, but you've actually used an independent test data set each time. So, you know, you've not got this, and this is especially important. Well, this is important on any size data set. It gives you that, you know, that statistical independence and the ability to use your entire data set. The other thing you want to vary as well is the parameters. You know, this is the nearest neighbor classifier in a Python package called scikit-learn. And you can see these are all the different parameters that you can pass to it. So one of the other things you would do is you would actually create a matrix of different parameters. So you might try it with 5 nearest neighbors, 10 nearest neighbors, 15 nearest neighbors. You may try it with uniform weighting or a distance weighting. And then there's different algorithms you can use to calculate nearest neighbors. There's different distance metrics. So what you can do is you can build up, if you like, different permutations of these parameters and then run those on your 5 different sets of data on 20 different algorithms. So you can see what ends up happening is we end up writing, or we end up evaluating hundreds of different combinations of models, parameters, and randomized data sets. So to sort of wrap it up in terms of a high-level algorithm that works really well in the machine learning data spaces, you know, your first step is pre-process your data. You split and train and split your training and test data sets. You don't actually do it here. You would do it in this loop somewhere, but I'll put it in there. You know, you've actually got to grab the right test data as I showed earlier. But then, you know, if you've got n algorithms, you step through n algorithms and you might have X different sets of parameters. You step through those and then you loop through your 5 different cross-validated data sets. Then you've come to the core of your algorithm, and that's to create the model using the current algorithm and the training data set. Then you evaluate it using the test data set, and then you record the model score. And then because you've now looped through all your data, you then either total or average whatever you're doing and however you're scoring it for all the sets of parameters. And then you've got, for that algorithm and that parameter set, you've got a score. Then once you've done that, you can work out what are the best parameters for this model. And then finally, your final step as you come out of there is now you've actually worked out what's your best model and what's your best set of parameters. And then you're done, you've found the right model for your data set, and you can put this model into production now. And when I mean put it into production, is typically you put that in as a service in a computing environment, a web service, and then you call that from other programs. So you can simply pass it your data, and it will classify your data for you and pass you back a prediction, okay? This idea here, this concept of the no free lunch, it's a bit like the arguments about different Kriging algorithms. At the end of the day, depending on where you are in the ore body, a different algorithm may work better than another algorithm. And maybe that's the type of approach you take. So not only do you pre-process your data and split it, you also then consider various areas of your ore body to make sure you've got the best predictor for a particular area. So finally, my last slide is all about, you know, where could you use this in geology? Well, there's loads of places you can use it. And I spoke to a few geologists when I was putting this together. Heath Arvidson the other day gave a talk on the self-learning ore body about 2 weeks ago. So certainly that concept of when you do estimates, when you do estimation, of course, you could use machine learning. If you combine that with spatial information like variography and machine learning, you could certainly use it there. And then when you get plant information or shipping information, whatever the case may be, you can feed that information back through that loop to have this overall reconciliation and have machine learning involved in various stages. There's also things like you could validate your logging, or you could even predict the material logging from all the other information you collect. So from assays, geophysics, spectral surveys, etc. You could do geological interpretation from that data. So you're taking all of that information in and manipulating it with machine learning algorithms and potentially other business rules as well that, you know, are expert knowledge from a geologist, for example. In the computer vision space, things like face mapping, core analysis, all that kind of stuff could be automated through a computer vision solution that's backed by machine learning technology. So they're just some of the ideas, and this was just a brief overview for about machine learning. So I hope it was interesting and that you learned something. And yeah, I hope there's a few questions.
Thank you so much for taking that time, Mark.